So here it's the same problem again, and let me also introduce these using complex numbers. It's the same problem in a slightly different way of solving it using complex numbers. Numbers here. You know this e to the 2x and cosine 3x kind of shows up in the polar form of a complex number, so we can try that and see what happened. And again, not many of you have a training in the complex analysis, so this might be just some magical trick, but it actually works. So if you just have to compute the particular solution, using complex numbers will be maybe efficient as well. The trick goes as follows: e to the 2x. Why don't I change that to the sine 3x? You can see this is almost the same problem, but it's a little bit different technique that you have to use for the complex case, so I think it's more meaningful in here. So I'm going to go ahead and change that. All right, that changed to sine 3x. So what we're going to consider is that this complex number that's such that this one shows up. So like this, cosine 3x, cosine is a real part of the complex number, and I times e to the 2x sine 3x. If you pair this up like this, together it's going to be e to the 2x times this cosine 3x, and sine 3x becomes e to the I times 3x, right? So altogether, you can use this exponential law of a complex numbers, and you can write 2 plus 3i times x. So that's a complex number. So rather than looking at right-hand side, this particular part of this polar form, we're going to consider all of them together in there and see what happens. So we're entering the world of complex number, allowing all the coefficient we're to try to play with is actually all complex numbers. So what we're trying in here is simply this e to the alpha. So I'm going to simplify e to the alpha x, where the alpha is this complex number 2 to the 3i. Now at the moment, treat it as if this alpha here is real numbers. And think about what happened if I stick this e to the alpha in here, what's going to happen. Because of the constant, whenever you differentiate this one, only this alpha as a constant is going to pop out. So it's going to be, after you go through, it's clear it's constant, though it's complex, constant times e to the alpha x. So we're sure if you try something like this, we will just end up at alpha a times e to the alpha x. Again, if you think about it, this one is a polar form of a complex number. It has these two parts. We have to compare with this what we have in the right-hand side and see which one really gives this sine 3x. So understanding that what kind of magic this one does is going to be clear, and we actually expanded this one into polar form. But remember, this has a real and an imaginary part. This one also has a real and an imaginary part. So although it looks like just one coefficient, we're actually looking at the two separate parts of the coefficients. So here's the left-hand side of this equation, which is differentiating this one, and I mean going through this operator, and that part's easy. Always you will have the e to the alpha x differentiating 2 times, so we have alpha squared, and e to the alpha x, you just factor it out, right? And when we go through this one, we differentiate 1 time is e to the alpha squared negative alpha, that's what it is, and plus, and not differentiating the 1. So left-hand side will give you this quick calculation. That's exactly what this is, a, the constant, times e to the alpha x. So let's, and we know what alpha is, and we're going to calculate this one if you square that. So I did it over here. If you square that, you have negative 5 plus 12i minus alpha is the 2 plus 3i, so this is going to be simply negative 2 minus 3i plus 1, and e to the alpha x. Okay, so simply this whole thing is going to be, so we get negative 6 plus 9i in there, times e to the alpha x. So let's further continue break down this one into real and imaginary part like this. It continues like this, negative 6 plus 9i times e to the alpha x is in this form, e to the 2x cosine 3x plus I times e to the 2x sine 3x. When you split these two parts into real and imaginary part, and we can compare now with the right hand side. So the real part is coming from multiplying these two real part, which is negative 6 e to the 2x cosine 3x, and also is coming from multiplying these two part with i's are involved. There's a negative as we multiply I times I, so we have 9 e to the 2x and sine 3x. So there's no I anymore. The rest of the part, other cross multiplication, will have I in it. So for example, if you multiply these two, we have negative 6 e to the 2x sine 3x. If you multiply these two, we have positive 9 cosine e to the x e to the 2x cosine 3x. So that's what we get. So I move things up a little bit. So we're going to compare this one with L of e to the alpha x. This is the result, right? That's why we have calculated e to the alpha x, written the real part and imaginary part, e to the 2x cosine 3x there, plus I times e to the 2x sine 3x. And if you think about it, if this is a real part and this is the imaginary part, the linearity still works. So if you compare this one with the result over here, I'm going to box it over here. So the box it, if you actually go through with a little bit of complex multiplication, or complex theory, and this is how it simplifies a real part and imaginary part. If you send this, if you just try this real part through this L, of course you're going to end up a real part. This is not going to affect that part at all. If you try this part, I is a constant, so I actually factors out. So L only affects this coefficient, which is real part, and it is going to give you exactly that shape. So we can conclude from this observation on here, nicely like this, using the linearity, if you send this cosine part through this operator L, you will definitely get a real function. But if you use linearity even over the complex, that's kind of hard to believe, but that's with a bit of training in that complex analysis part, that this works in this way. And that's the real function, and that's another real function. If this equals this yellow thing there, yellow box, up there, it must be the case this e to the 2x goes to that real part, and e to the 2x, the sine 3x part, must correspond to this imaginary part. So we have these answers. So namely, we have a statement is L of e to the 2x cosine 3x. It's going to be the real part, negative 6 e to the 2x. Sorry about the interruption. That's why, so this real part matches the real part of this yellow box. And if you look at the imaginary part, L of e to the 2x sine 3x, that is going to match the imaginary part there, like that. So we have this result. So if you want to get rid of cosine or sine, you can multiply the appropriate constants here to get rid of one of the terms. So slide it up here. So once you reach this part, the rest of the part is the same as the previous method we did. Once you have this e to the 2x cosine 3x, e to the 2x sine 3x result came out like this. Another trick that is often introduced here is using the complex, it's still the complex method, and using the complex conjugate. This method goes like this. Remember, we call that alpha. That's the number associated with this polar form was a 2 plus 3i. Its complex conjugate, we're going to denote it by beta, is 2 minus 3 times I. And if you look at the polar form of these two things, they have exactly the same component except a slightly different sign. So linear combination of these two, for example, alpha times e to the alpha x plus b times, not alpha as a, and b times e to the beta x, if you try that, like this, there must be complex numbers a and b that match any form you want. For example, what we want here is the 2x times sine 3x. And you can realize that how to write the sine 3x in terms of alpha and beta is the following. If you look at it here, e to the alpha x, that has, and then you compare with e to the beta x. And if you think about the real and imaginary part of these two conjugate complex numbers, we want sine things to be survived, so if you subtract that, then cosine part with the same sign, the negative argument doesn't change the cosine part, and if you divide it by 2, and that's exactly what this part will be. So here I'm going to verify this part is e to the alpha x cosine positive 3x, and this one has e to the alpha x cosine of negative 3x, but these cosine is an even function. These two things are the same, so they will cancel. And it has imaginary part sine 3x, and this one has imaginary part sine negative 3x. But because of the negative, an odd sign is an odd function, they will cancel. That'll give you 2 copies of these, and we want only 1 copy, and it's going to look like this. So what happens is that we have to go through this operator with this 2 separate term. Then you will have, this part will be a prime, which is in terms of a and b, and that'll involve some arithmetic on 2 and 3 and negative 3. And when we go through the operator, so that will be the coefficient of e to the alpha x, that is written in terms of capital A and capital B, and this will be also written in terms of capital A and capital B of, actually I was wrong about that, this A prime is solely in terms of A, B prime is solely in terms of B. They don't interact each other, and here we're using the fact that this e to the alpha x and e to the beta x is linearly independent, so that must be 1/2 e to the alpha x in that case over there, minus negative 1/2 e to the beta x. That was on the right hand side. So it must be the case after you went through, a prime must be, realize that I forgot, and here we have 2i, so we have to divide this whole thing by I there, so I'm missing I in there, so I'm putting back in here I, so that not only is it 2 copies of I, it's a 2 times I, so we have to kill that 2 times I. So we have i's in the denominator. Let me fix that. And here, this is 1 divided by 2 times I, 1 divided by 2 times I. So a prime must be 1/2 divided by 1 divided by 2i, and b prime is negative 1 divided by 2i. So you will get these complex numbers in front of 2 alpha x and 2 beta x after you go through the operator, and you have to set these two things equal to each other. From there, it's a separate equation, and it's not a and b and mixed together, so you can figure out what a and what b is. So this is completely using the complex conjugate method. I don't find, although this is interesting and fun to do, I don't find this necessarily more efficient than what we're doing with this much of a complex calculation. So I'll just do this much, and I'll stick to this method of complex numbers.